All right. So we're going to try to start at the beginning and see if we can comprehend what's going on with radioactivity. Okay. Now, if you're going to evolve something over time, you're going to need a lot of time. In fact, the age of the Earth has about doubled every 10 years since macroevolution became a common method for a common explanation of origins. Okay, so back in Darwin's day, they thought the Earth was a lot younger, and yeah, they keep making it older. They haven't in a little while, mostly because the media has been ignoring that. There's a lot of scientists, for example, that are pushing for an age of the universe beyond the 13.5 billion years. And they're trying to say that the universe is more like 20 billion years old or maybe 50 billion years old. And I've even heard numbers as high as 100 billion. One of the reasons why they're pushing for the age of the universe to be older is we found these things they call Methuselah stars that are apparently older than the universe. We'll talk about all that coming soon to a PowerPoint near you. Okay, so what evidence exists to support an old Earth, and what evidence exists to support a young Earth? This is perhaps one of those things like a global flood. If there was such a thing, it should be really easy to show that, right? I should be up here like quoting the Bible. Oh well, you can take the Bible seriously because that's what the Bible says. Now you should be able to go out there and dig a hole and find evidence for this. Okay, it shouldn't be, you know, all that difficult. So we ought to be able to tell, right? That's a super famous quote. Actually, sorry, that's one of my quotes. All right. So what are some common ways to measure the age of the Earth? Well, there's actually a lot of different ways that you might measure the age of the Earth. One would be radioisotopic decay. So some elements are unstable, kind of like your mom. sorry, no. Your mom is perfectly stable, or she was before she had kids, right? Having kids makes you unstable. Before the snowpocalypse? Oh my goodness. I'm gonna get letters about that one. I don't mean it like that. I'm just kidding. I'm telling Cartwright. All right. So some elements are really unstable. No, like seriously, they explode every once in a while. We'll talk about why.
What element would that be?
Everything bigger than lead.
Really? Milk.
Yeah.
Wait.
Milk is made of 100% things that are smaller.
So bigger things than lead. Can I have like one bigger as in like
more massive than atom is more massive.
Yeah.
Yeah. In fact, there's even radioactive types of lead. So some flavors of lead are radioactive. No, not usually that dangerous because lead being so dense absorbs the particles that they emit. So
that's why they use lead.
That's a seal. Oh yeah, it'll absorb about anything. Anyway, you could look at tree rings, right? Dendrochronology is perhaps, you know, this idea you have of scientists living in society life, and you know, they carry around test tubes, they can blow things up. Nah. Most scientists live an incredibly boring life. We looked at an example in zoology this week of a dude who spends all his time measuring fish scales under a microscope and counting little rings, putting them in the little envelopes and cataloging them in this giant file of 23,000 fish scales that he's got over there. And I'm just like, dodge the bullet with that one because not exactly the exciting career you might have thought. Anyway, so counting tree rings. Wow. How bored are you?
Well, you just got to know how to count.
Yes. Anyway, so you can count these guys up. Dendrochronology. You can take a core from a tree, which doesn't really hurt the tree as far as we know. Little drill, keep the center of the hole, and count up the tree rings. Get a very good idea of how old it is. Here's the thing: we know for a fact that some trees grow more than one ring per year. Okay. So you might look at the rings and be like, okay, so the small rings are winter growth, the wide rings are summer growth. That's not really true. you got slow growth, fast growth, slow growth, fast growth. You don't know if it's summer, winter, summer, winter. You get like 5 summers and 8 winters every year in Oklahoma. So some trees grow more than 1 ring per year, and it's just fast and slow growth. You don't know if it's summer or winter. So we know for a fact that dendrochronology overestimates the age of some trees. And the way we know this is you can actually compare, like you can see like scarring from fires and stuff and compare different trees and figure out that they have different rings like after, okay, they all have this, they all survived the same fire. They have different numbers of rings after that, okay? So for example, we find tree rings sometimes going back like something like 8,000 years, maybe even as far as 10,000 years. Again, that's probably an overestimation, but it's an excellent question. Okay, so it's been 30,000 years since the last ice age. How come we don't find a bristlecone pine tree out there that's 25,000 years old? These guys don't show any signs of slowing down. They don't seem to age. So how come we don't find a bristlecone pine tree that popped up right after the last ice age? Why don't we find an older one? In other words,
What do you believe the Earth's age is?
I'm convinced it's somewhere between 6 and 10,000 years.
Okay.
Dude, but that's just my opinion. I wasn't there when it was made, so I don't know. Right? Erosion. Okay. Did you know we actually have very accurate measurements for how much land we're losing? We're losing a lot, actually, through erosion. Now, if we don't behave ourselves, we lose a lot more. Okay, we learned that in the Dust Bowl, didn't we? Yeah, humans can really cause a lot of problems when it comes to erosion and removing trees and plowing up land and doing all that kind of stuff can really cause a lot of problems if you don't know what you're doing. Okay, so we have very accurate measurements with rivers and all that stuff about how much sediment is getting dumped into the ocean every year. And here's the thing. If you do the math on this, you'll figure out the entire Earth will erode down to sea level in like 14 million years. Now, that sounds like a long time, but you sort of look at that and you're like, well, that's a blink of an eye compared to 4.5 billion years that we're supposed to have lived on this planet. So where's all the new land that should be popping up?
Well, that's why we're going to colonize Mars.
Yeah, that's where we got to bug it up here, man. This planet's getting a little crazy. Yeah, and that includes all volcanic activity, all the earthquake activity that produces new land.
That was very interesting.
It doesn't make it land fast enough to compensate that. What's that?
I said I was very interested in the Mars rover finally landing.
Now you know it's a robot planet, right?
Yeah.
The whole planet's populated by robots. So we can measure erosion. We can find a lot of weird stuff about this whole erosion thing, right? Because the weird thing is, the ocean basins are made of igneous rock, but the land is covered with sedimentary rock. What is up with that? The Himalayan mountains are sedimentary rock, 30,000 feet above sea level. Why is all their igneous rock under the ocean and all the sedimentary rock on top of the land? That doesn't make any sense. Okay, there should be about 30 times as much erosion in river deltas and things like that and down at the bottom of the ocean than there is. There's not nearly enough down there to have allowed for millions of years of time. We can look at the growth of river deltas. We can look at the accumulation of salt in the ocean. The ocean is constantly getting saltier. We can measure that every year. Go back in time, somewhere like 70,000 years ago or something like that. I forget the exact number. The ocean has no salt in it at all. We can look at the decay of the Earth's magnetic field. It is constantly getting weaker. A lot of scientists believe that once it reaches a critical point, it actually flips. That doesn't make any sense to me, but they all seem to agree about this. The young Earthers, the old Earthers, everybody. So one of these days I'm going to find a really smart person and have them explain it to me. But anyway, the Earth's magnetic field is decaying. That might put a limit on the Earth's age. And then again, it might not. Maybe it just goes through cycles.
We have to lose mass in the Earth.
I don't understand it at all. I'll be perfectly honest with you. I can understand that, okay, if the Earth was created with a magnetic field, then that field would lose strength over time. That makes sense to me because the Earth's core would resist the flow of electrons, right? Like everything does. So it gets weaker and weaker. And we can see the Earth's magnetic field getting weaker and weaker the whole time we've been measuring it. So that makes perfect sense to me. The problem, of course, is if you go back in time, about 10,000 years ago, the magnetic field of the Earth would have been so strong, it would have ripped the iron out of your blood. That's a problem, by the way. Okay, you don't want to be messing around with that. It also would have created an electric current going through the core that would have blown up the planet, which is also enough to ruin your whole day. So it can't possibly. I mean, if the magnetic field just gets weaker and weaker to zero, this puts a pretty hard limit on the upper age of the Earth. Again, a lot of people think that it's cyclical and it gets weaker sometimes and it gets stronger sometimes. But all we've ever observed is the thing getting weaker. So anyway, the recession of the moon. Did you know the moon is getting further away every year? We can measure the distance from the Earth to the moon with an incredible
1 yard
accuracy. You know what?
It's in 1 yard stick.
We do it with radar. We bounce radar beams off the moon and we can time
That would not
be how long it takes to get there.
That would not be the best thing if we just honestly.
Well, it is getting away. It won't actually escape. We'll talk about why.
So fast.
But it is getting further away, and we can, and again, that puts a hard limit on the age of the Earth and Moon system. The sun might be shrinking. That is possible that the sun is shrinking. You could measure dust accumulation. There's lots. Anyway, my point is, there's lots of different ways to try and measure the age of the Earth. It's not just radioisotopes. The reason why you never hear any of those other things talked about on National Geographic is because there's only one way of measuring the Earth that gives you an age in the billions of years, and that's radioisotopes. Okay. Now, when it comes to radioisotopic dating, this kind of thing is oftentimes presented as absolutely unquestionable, irrefutable evidence that the Earth is really old. And that always makes scientists very skeptical. You got a scientific bone in your body, and somebody presents you what they think is irrefutable, watertight, ironclad proof. You sort of go, wait a minute, why are you so bent out of shape about this? I mean, isn't science always done with an open hand? I mean, don't we always say, well, we don't know anything for sure, but here's the evidence that seems to indicate, X, Y, and Z. Right? So anytime they get to be hardcore, dogmatic, you might say religious about something, your red flags start going up, and your little warning sirens start going off, smoke might start coming out of your ears, and all the ears start trying to go, wait a minute. What do you mean irrefutable evidence? There's always a chance you could be wrong about something. I mean, surely you admit that as a scientist, right? Oh, no, we're very sure about this. Okay. Let's examine it. Now, one of the first things you got to realize is there's lots of different flavors of radioactive isotopes, okay? And they all have their own characteristics, right? So, for example, carbon-14. I'm sure you've heard of carbon-14 dating. It is commonly done with organic substances. So, for example, you dig up the ruins at Kiribati in the Haas, right? Have you studied that before? The ruins of copper. Kiribati and the Haas means ruins of copper in Arabic, I think. Those were Solomon's mines. That's where he got all his wealth from. Okay, so you can dig up the slag heaps at Kiribati and the Haas, find little pieces of charcoal that they use to melt all this copper ore, refine all this copper ore, and you can test it with carbon-14 dating because it's an organic compound and it contains carbon. Okay. And you can figure out, you can figure out when the slag was laid down, sort of. Carbon-14 tends to be accurate about 2,000 or 3,000 years ago. After that, it starts getting really ridiculous. So, for example, you can take a carbon-14 date of a mammoth's tusk and a carbon-14 date of his butt, and you figure out the tusk is like 26,000 years old and his butt is like 35,000 years old. So that's either a really slow growing mammoth or something's not right. It's also, being carbon, it can be washed out of things pretty easily. So if you've got a lot of water present, That might not work out so well for you. There's rubidium that decays into strontium. There's thorium that decays into lead. There's uranium that eventually decays into lead. There's potassium that decays into argon and all those kinds of things. So it's not just any element larger than iron that is, excuse me, any element that's larger than lead that is radioactive. There's other things that can be radioactive too. So carbon, let's look at that as just an example. You're most familiar perhaps with carbon-12. Carbon-12 has 6 protons and 6 neutrons. It's stable, all right? It doesn't blow up. There is also 1 in a million or so carbon atoms. It's carbon-13. It has an extra neutron. It is also stable. It sits there. It doesn't really do anything. Okay. 1 in a billion or so has 2 extra neutrons. That is carbon-14, and it is unstable. What do we mean? We mean that every once in a while, you have a gajillion of these atoms together, a certain number of them per hour or per day will actually emit a particle, okay? The neutron, there's 2 extra neutrons, one of them will spit out an electron and become a proton, okay? So a neutron, if it spits an electron out, it becomes a proton, and it spits out some other stuff too, but mainly just the electron, okay? This electron is what we call beta decay, all right? You can stop the electron with a sheet of aluminum foil. So yes, it's radioactive decay. Yes, it's very scary, and oh my gosh, we're all gonna die. Well, you can stop it with a sheet of aluminum foil, so really not all that dangerous. Beta decay. Things that beta decay are only dangerous to you if you like eat them or something like that.
That sounds
Right?
delicious.
Delicious beta
They
decay.
said they come with a lot of different flavors.
Yeah,
Right?
yeah.
It's flavor.
It tastes like metal. Death.
And radioactive.
Yum.
Yeah. And by the way, you are radioactive. You have a tiny amount.
A banana has a tiny amount
It does,
of
though.
radioactivity.
Because biological systems can't tell the difference between the various isotopes of carbon. They all have the same chemistry. Okay, so chemically they're identical. They make the same molecules, have the same melting point, same boiling point. All that stuff is identical. So your body, your cells can't tell the difference. And there's carbon-14 out there in the wild. And so you eat some of it and you're incorporating it into your cells. And this is also why bricks are slightly radioactive. Not very though. The radioactivity levels are extremely low and like nobody worries about it, okay?
So if you sleep on breaks, you'll be.
Do what?
What happens if you sleep on breaks?
Yeah, nothing. Granite countertops, radioactive. Not that radioactive, though, right? They don't really cause many problems. Yeah, you wouldn't be able to cook the chicken with the granite countertop.
No, I mean like kind of that before you put it on the
Yeah, it doesn't. It's such a low level of radioactivity that it's just harmless.
I put it on my tray, radioactive.
Yeah. You could grill the thing on a like a nuclear, like that's possible.
What about if you brought it to your
No. Okay, so most of the time radioactive decay emits particles that are energetic enough that they just like kill your cells. They don't really add like thermal energy to you. Okay. Or they mutate your DNA.
Someday there's a problem.
Yeah. All right. Okay, so you guys are familiar with the fact that everything that is physical, let's say, is made up of atoms, all right? And therefore they have a chemical identity. Okay. You're familiar with the structure of the atom, that you have an electron orbitals, quote unquote, that hover around the nucleus in energy levels that are, well, not really like orbits. They're much more like satanic clown balloon things. Let me show you. Okay. So maybe we should have warned you guys about this before you came to class, but atomic orbitals end up being so strange because the electrons are all attracted to the nucleus, electrically, okay? They have the opposite charge, but they're all repelled by each other, okay? So it turns out that this first orbital is not a circle, but a sphere that exists around the nucleus. And this one is a larger sphere, okay? And it ends up compressing the orbital beneath it. And then you get these weird kidney bean looking things. And let's scroll down here to the one that I'm looking for. There we go. So it turns out that as you stack these guys on top of each other, they repeat themselves, and then the kidney beans start getting really freaky, and then we get donut shaped ones.
Whoa.
As you build up their complexity. Keep in mind, this is just stacking on top of itself. Okay, so you got all the complexity we just saw underneath, and then the outside orbital happens to be a sphere again. So this is why sodium and potassium, for example, behave basically the same, right? They're right on top of each other in the periodic table, and sodium and potassium make the same molecules. You can have sodium chloride, you can have potassium chloride, and you can't really even taste the difference hardly. Okay, they're salty, right? And then you get those guys again. Salty, yeah. And then the donut-shaped ones, which are more like a yeah. And it just gets worse. It just gets worse. And it just gets worse. Oh, and then it starts over again. So these orbitals stack up. All right. So in other words, they're not circles. They're not orbits. Really, they're crazy. Okay. So the other thing you got to know about atoms, they're infinitesimally small. How small are they? Great question. A speck of dust is roughly halfway between the size of an atom, which an atom looks nothing like that, okay, and the size of the Earth. All right.
So give me like a.
So if you can understand that it's impossible for you to understand how many specks of dust it would take to fill this room, and you can understand that it would be impossible for you to understand how many specks of dust it would take to cover the state of Texas 100 miles deep, and you can understand that it would be impossible for you to understand how many specks of dust that it takes to build a planet the size of the Earth.
And then times it by 2.
That, no. So roughly the same number of specks of dust it would take you to build a planet the size of the Earth is the same number of atoms within the speck of dust.
Oh.
Okay.
That's weird.
There's a lot of them in there. Okay. Now,
So 2 specks of dust is. Okay.
And the number of atoms in there. If you had that number of specks of dust, you could build 2 planets the size of the Earth.
It'd be 1, right? Because if it's half.
No, it's in between.
Give
So
me
speck of
a
dust-
math equation, not a science equation.
Okay. So you could say that a dog is halfway between the size of an elephant and a blue jay. Okay, speck of dust is halfway between the size of an atom and the size of the Earth. So the same number of blue jays it takes to create a dog, is the same number of dogs it takes to create a whatever. So this is the same number, all right? But in other words, there are quintillions and quintillions of atoms in that speck of dust. Now you might ask me, well, wait a minute, how do we even know that atoms exist? We do. It turns out that they are way too small to see, all right? In fact, they're so small, they are smaller than a visible wavelength of light, which is why we use X-rays to try and determine the structure of molecules, right, with X-ray crystallography. Okay. I can assure you that atoms exist. I have personally done hundreds of experiments that demonstrate that fact.
Wait, then has it? So you can't possibly see an atom.
You can detect them.
You can detect them.
It's similar to the way that you can't see your brain. And so how do you know you have one? Well, you don't. Of course you know you have a brain. You can detect it. It makes electrical signals, and obviously if you didn't have a brain, you couldn't function, right? You can't see the wind either, but you can detect the wind, right? You can see the effects of the wind, right? So we can detect these little buggers with X-rays and with gamma rays, and we can know things about their structure, and we can do experiments that show and prove that they exist. All right. Hopefully, your physical science teacher did something along those lines. If you take my chemistry class, I'll prove to you that atoms exist. Anyway, suffice it to say, it's one of the most well-established, and we can actually see them with like X-rays and stuff. Okay, so they're very, very, very small. So enough uranium to have a marker like this or a pointer like this would contain multiple, trillions upon trillions of atoms of uranium. Okay. So, the nucleus of the atom is tiny, and it's made of protons and neutrons. Now I know what you're thinking. Now wait just a second. I happen to know, using my highly educated brain, that positive charges and negative charges repel one another. You just got done telling us, Card, right? That all those electrons up in those clouds repel one another. What's going on with the protons in the nucleus? If the protons in the nucleus repel one another, then everything bigger than hydrogen should blow up. Right. And so we actually did experiments on this. Okay, Rutherford did experiments on matter. He blasted a sheet of gold foil with alpha particles. He knew that alpha particles were positively charged. And so his theory was that he was going to blast this gold foil with alpha particles, and it was going to scatter alpha particles to kingdom come, and he'd be able to detect them on a special detector that he put up. And that is not what happened. The vast majority of alpha particles went right through the gold foil and hit the other side, and there was this huge over-solarized exposure on his detector. Only a tiny fraction of them were deflected. And so he was like, guys, you know what this means? This means that all the positive charge in the atom is concentrated in a tiny, tiny area. And he calculated how big the thing was. And he was like, this thing is infinitesimally small. Like, what is going on here? And somebody said, well, you know what this means, right? This means that there's got to be another force that we don't know about yet that's holding the nucleus of the atom together.
Gravity.
Not gravity, way stronger than gravity. We call it a strong nuclear force, okay? So it turns out that the strong nuclear force, if we've got this right, and we think we do, the strong nuclear force is incredibly strong. It's unbelievably strong. It's ridiculously strong. It is something like 100 times stronger than electromagnetism, which is roughly 100 billion times stronger than gravity. Okay, the strong nuclear force, yeah, we call it what it is. It's ridiculously strong, and it is very short range. Okay, you cannot have the strong nuclear force existing between me and my coffee mug over there.
So what would happen
It breaks
if
down.
the atom was the world and like the gravity?
Right. If you're trying to equate gravity to electromagnetism, it doesn't really work.
Well, what would it do to us if we were staying?
So for example,
if it was
if you could expand the size of an atom to something you could actually see, right? So let's say you made the nucleus of a hydrogen atom the size of the ball bearing on this ballpoint pen. Okay, it's pretty small. How far away are the electrons? Well, if you put this in the middle of a stadium, like a baseball stadium or something like that, the first electron would be on the outside of the stadium. Okay, atoms are almost completely empty space. What holds them together? Electromagnetism. And what holds the nucleus together is the strong nuclear force. So what holds the universe together? Not gravity. It's a strong nuclear force. Okay. So you've got all these positively charged particles. Anything bigger than hydrogen, that is. Let's look at helium. Right. Helium has 2 protons and 2 neutrons, most of it. Right. And it just so happens that the protons are so close together that they overcome the electromagnetic repulsion that electromagnetism tells us they experience, and the strong nuclear force takes over and binds them together with an unbelievable force that's basically indestructible. You can overcome it if you put them in like the core of a star or something, but pretty much you have to do horrible things to an atom, like accelerate it to 97% the speed of light or something like that, in order to overcome the strong nuclear force and turn it into something else. You can technically turn lead into gold. We did it one time.
Is that
for fun.
is that like the same thing where they'll shoot those things through?
Oh, yeah.
And like
In the mass particle collider
turn
and stuff?
coal into diamond or something.
Oh,
like
yeah.
that. Yeah.
Actually, turning coal into diamonds is really easy
Particle
compared to this.
accelerator.
Yeah, yeah. So they turned lead into gold one time just for fun. It's way cheaper to just dig it out of the ground. Anyway, so the strong nuclear force is incredibly strong and it's incredibly short ranged. It has to be both of those things for the universe to exist. Because here's the thing: if you made the strong nuclear force very long range, you'd be able to build atoms that were very, very large. This is a problem for you because most of an atom is, as you know, is empty space. So if you start building atoms that are very, very large, they start having a lot of gravitational force, and basically the entire universe collapses into an omnimassive black hole. Okay? So the strong nuclear force has to be the exact strength that it is, and it cannot possibly be any longer range than it is, right? So in other words, a proton over here doesn't experience the strong nuclear force. It's too far away. It experiences electromagnetism and it races away from, they just fly apart from each other like trying to force two north poles of a magnet together, only hundreds of times stronger than that, all right? So what happens as you work your way up the periodic table? You're constantly adding protons, right? Carbon has 6, oxygen has 8, right? You get up to iron has, 20 something? Something like that. And you're constantly adding more and more protons to the nucleus. Okay, well, this is fine up until about iron. After iron, things kind of start breaking down a little bit to the point that once you get to lead is, 82, right? 82 protons. So anyway, in other words, this thing is getting bigger and bigger and bigger. And all of a sudden, these guys over here, these protons, really don't like those guys over there, right? You can understand that as this thing is increasing in mass, now you have a tug of war between the strong nuclear force trying to bind the nucleus together and the electromagnetic force that is trying to rip it apart, okay? So smaller atoms are very, 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 very stable, but as they get larger, you have this problem, okay? We call that instability radioactivity. That's what radioactivity is. It's an instability in the nucleus where really the strong nuclear force is breaking down. We're right on the edge of its ability to hold the nucleus together, and every once in a while it will lose, and you'll have radioactive decay.
Why does large amount of radioactivity bother us if it's just on something of a tug of war? Why does it bother us to go into a place that has?
Oh, because of radioactive decay.
Decay.
It's not the instability that hurts us. It's the result of that instability, right? So it's not gravity that hurts you. It's the rock that falls on you, right? It's the particle that's emitted. It's the result of that instability that causes us problems, because it turns out radioactive decay ends up releasing particles that are moving at a crazy level of speed, and they'll rip you apart. So it's radioactive decay that's a problem. We usually describe radioactive decay as 3 basic flavors. You got alpha decay, beta decay, and gamma decay. Turns out there's lots of other types of radioactive decay as well, and other particles that get emitted. But those are the 3 major ones. Alpha decay is really easy. That's stuff that's a helium nucleus that gets spit out by alpha decay. They don't last very long. They rip electrons off of something and they become helium, and they're perfectly harmless little adorable fluff balls. Okay. Beta decay is a little bit more dangerous. In that case, you're emitting a beta particle, which is just an electron. Okay, you're spitting it out pretty fast, and it can actually get through, like a whole textbook or something like that. You can stop alpha particles with a single sheet of paper. right? They don't get through your skin. They don't cause you problems unless you eat them, okay? Beta decay ends up being more of an issue, and it will get through like maybe an entire textbook worth of stuff before it finally stops. The real problem is gamma decay. Gamma decay is a very high energy photon, like much more energetic even than an X-ray. And we think there might be gamma rays out there that are so energetic they would go right through the Earth. Obviously, they'd be impossible to detect, but you know, that's the gamma decay will get through several inches of lead before it's finally stopped. So X-rays are stopped by lead, not gamma rays. Okay, gamma rays will go through lead. So if you could see in gamma rays, you could see through much of the Earth's crust.
Go about making a gamma ray.
Very carefully. Well, it's just the way that the nucleus gets rid of all this pent-up energy that it has.
So the larger, so if you have a very massive thing,
yeah,
it is going to create a more dangerous
right
production.
Right. So carbon-14 never emits a gamma particle. It's only the beta particle, and it's basically, you know, you don't care. You know, it's 1 in a billion atoms anyway, right? So it's not dangerous radiation, right? So it's important that you understand. A lot of, well, hopefully none of your people, but some homeschoolers are really worried about 5G, right? And they have no concept of non-ionizing radiation. Like, what part of non-ionizing radiation don't you understand? It's innocuous. I'm old enough to remember when they said, "Oh, cell phones emit radiation." Oh, they're bad.
We emit radiation.
Yeah, we emit radiation too. What part of non-ionizing radiation do you not understand? It doesn't hurt you, okay? Maybe extreme. Okay, yeah, if you went up and sat on a radio antenna, you know, at however many watts that is, that might be bad for you. I doubt it. Anyway, so yeah, it's non-ionizing radiation. It doesn't destroy your cells. It doesn't destroy your atoms. You're fine. Okay. Anyway, so it's not considered dangerous radiation. Dangerous radiation levels, oftentimes we're worried about those gamma rays, right? So this is a great time to talk about the fact that I'm not worried about them dumping radioactive waste into the ocean, as long as they treat it correctly. For example, the Fukushima, they have all this, you know, radioactive water that they had to use to cool down the reactors, and they're storing it in all of these tanks. Well, the Japanese are pretty smart, and they figured out ways to remove all of the radioactive contaminants except tritium. Tritium does a beta decay, and it's actually one of the weakest beta decay particles ever. And I think the Japanese ought to just dump all that stuff in the ocean. I don't think it would cause a problem at all. Everyone's like, "Oh my gosh, you're dumping radioactive water." Calm yourself down. Just study it a little bit. There's a reason why that's not a big deal. Anyway, so we need to learn something from the Japanese and how to filter water properly. Huh?
What can it hurt if it's really weak?
Probably nothing. Yeah, you throw a tennis ball and it gets out the door. How many tennis balls would you have to throw to damage that door?
Depends on what kind of.
It's like, I know how to build a potato cannon. We can get this thing up fast. Well, it's a higher energy level, right? The tritium always spits out the same energy level. That's another important thing about radioactive decay. When they decay, they're going to spit out an alpha particle that's the same energy level.
But if you had a lot of
Oh, sure.
Now, say they were dumping.
Yeah, you could dump enough tennis balls on somebody to really hurt them, you know, right? So you'd want a very dilute, right? So for example, if you were dumping it in the ocean, that'd be like the definition of a very dilute concentration of radioactive particles, right? Okay, so this is what radioactive decay is. You have this huge nucleus over here made of protons and neutrons. These guys over here don't get along with those guys because electromagnetism is starting to become the dominant force there. It makes an unstable nucleus, and every once in a while, it boots some of its members out, okay? This is called alpha decay. Uranium goes through alpha decay, and it actually demotes itself into other substances. Weird, right? So uranium eventually decays into lead after a long period of time. But it goes through lots of alpha decay to get there.
Return it back into
hit it with enough energy, right? Which is why bombarding things with neutrons will sometimes stimulate radioactive decay, right? So that instability is radioactivity. Some materials are less stable than others, okay? But and yeah, PowerPoint making a joke about your mom's not stable. Like, okay, humans are not as stable as you might think they are. None of us are. We just pretend that we are. So this causes the atoms to fall apart. They spit out particles, they spit out energy, they get mad at you, and they start, tearing things up. So we can actually measure this. Carbon-14 has an instability. We say it is we measure this instability with a half-life, right? So if you have a certain amount of carbon-14, how long before half of it has kicked the bucket? Because it's kind of a random process, right? You don't know when an individual atom is going to blow up. It's just they're unstable, so some of them just blow up. Certain number of them. Okay, so this is a measurement of the stability of it. So carbon-14 is actually really unstable, so much so that a half of a sample will decay in 5,730 years. Now, we didn't sit around for 5,730. No, we have a sample of it. We figured out how many of the things decayed. We have this little detector around it. We figured out how many of them decayed in a given length of time. This is very good laboratory research. I have no problems with any of the science that's going on here. We've been doing it for decades, and it's some of the best science out there. All right. U-238 has a half-life of 4.5 billion years. So it is way more stable than carbon-14. Okay. So these decay rates are very well understood and constant with a little asterisk. In the present, we are able to measure it with a great degree of accuracy. So since we know how long it takes half of the sample to decay, we can measure how much of that is in the substance versus how much of whatever it decays into, and get an idea of how old the thing is, right? So if it's, a quarter of it has decayed, we only have a certain number of years that have passed since the thing died and it stopped, eating things that had carbon-14 in it, right? So in potassium to argon, potassium decays into argon, and the argon becomes trapped, we think, inside the rock. And so we think that we can date from the hardening of the rock. So potassium argon is a very common way of dating igneous rocks. And that's another important thing to realize. If you're dating something that's organic, you would use carbon-14. If you're dating an igneous rock, it doesn't have any carbon in it to speak of. And so you wouldn't use carbon-14, you would use maybe potassium argon or something, a different dating method that might be more appropriate, okay? So we have to make assumptions. We always make assumptions in science. So surely the scientists that are doing this know what they're doing. They make good assumptions. Well, let's look at the 3 assumptions they have to make, right? First assumption is that there's no contamination, no additional parent or daughter element entered the system. Assumption number 2 is constant rate of decay. And assumption number 3 is no original daughter element. Now, all of your government school peers, they get taught this stuff. I very seriously doubt they get taught this at all. But let's just say they do. And, they're coming up against this stuff. And I guess they've been trained their whole lives to just whatever's in the textbook must be true. And, they don't question this? Really? How about that no contamination one? All right, this is a clam, fossilized clam. It's been buried under 2 miles of sedimentary rock. The evolutionists think it's been there for 200 million. What are the chances that it hasn't ever been dirty? Hey, seriously, who's thinking of this stuff? This is the problem with scientists who spend all their lives in a lab somewhere in sterile conditions, their fancy equipment. They never had dirt underneath their fingernails. Can you get any more naive than to assume that something that you think has been on the surface of the earth, buried under 2 miles of sedimentary rock, hasn't had any contamination? You want to run that one past me one more time? You know, if you believe that, I got some beachfront property in Kansas I'd like to sell you. Like, really? No contamination? Okay, all right, fine.
That took you like.
So long.
Wait, Kansas is landlocked. Oh. It's like there used to be a scam about buying property in Florida. They sell you this property in Florida that's really cheap, and you had to buy it like on the spot. It's just a special sale and stuff. They didn't realize they were selling you like swampland. Like, it's not all beachfront property, bro. Anyway, so let's start. That's kind of an old joke. Alligators. Alligators. Hope you like mosquitoes. They assume constant rate of decay. Now, I'll give them that one. The decay rate is very constant in the present. So they have every reason to assume it's always been constant. Except maybe it hasn't, and I'll show you probably next week that, yeah, I don't think it's been constant at all. And the whole thing about no original daughter element, how would you test that? Easy to test it, people. You go find some volcanic rock that got burped out of the volcano yesterday, and you take it to your lab and you test it. Is there any original daughter element? Turns out, in 100 out of 100 times, yes, there is original daughter element that is already present. So when the potassium is decaying into argon, unfortunately, there's already some argon there, which means that you get a rock that was born 20 years ago. You can take it to a lab and they will say, well, this is 3 million years old, because they're looking at all the argon that's trapped in there. They assume that all of it evaporated out when the rock was lava. That is not a good assumption. There's always original daughter element that is there, and sometimes it can get washed away because of contamination. All right, so we'll talk more about radioactivity next week, and we'll look at how this science, if you want to call it a science, gets done, or maybe why Cartwright doesn't think it's all that big of a deal. Right, I have some more for you.
I thought you were handing out homework for a second. I was like, ooh. Homework.
Turn in. Marvin, did you bring anything? Marvin, wait, you did? I'm going to send you an email tonight.
Okay.
I've been fine, I'll be back.
She don't see me. I don't email you. Yeah, my mom was on the phone with it one time.
All right, guys. See you next week.
I can understand this.